The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Take a look at the kinetic theory of gases on the next slide. Let's go over a few definitions that are going to be important for us. Beginning here with the kinetic theory of gases, also known as the kinetic molecular theory, is a set of assumptions that describe the nature of gases. Translated to mathematical form, it yields the ideal gas law equation, which describes the quantitative behavior of gases. Furthermore, what is kinetic energy? And as it says here, is the energy an object possesses due to its motion. Great. Now let's get started and take a look at those assumptions. Fundamental assumptions for the kinetic theory of gases. Beginning here with our first one. Gas particles consist of atoms or molecules that are in constant random motion throughout the volume they occupy. If you take a look down here at figure 2.21, not only are the gas particles going to be in constant random motion, but there is going to be considerable empty space between the particles, as we see here. Now, coming back up here, next, the volume of gas particles themselves is negligible compared to the total volume of the gas. Third, gas particles behave independently from one another. Thus, no attractive or repulsive forces exist between our gas particles here. Great. Next, collisions between gas particles and walls of a container are perfectly elastic. Therefore, kinetic energy is transferred without loss from one particle to the next, meaning that the total kinetic energy is going to be constant at constant temperature. Now, similarly, if we look here at figure 2.22, the elastic collision that's going to be taking place, this gas particle, as it leaves the wall here, is going to have the same kinetic energy as it did before it hit the wall, as we see here. Great. Let's move on to our next fundamental assumption. Average kinetic energy of a gas particle is proportional to the substance's temperature. Now, to explain that, let's take a look here at figure 2.23. And as we see here, as heat is being added to our gas particles here, they're going to absorb energy, as we see here. And a portion of that energy that's going to be absorbed is going to be potential energy, which does not raise the temperature. But the remainder of that energy is going to increase the kinetic energy, and meaning the speed. And as that kinetic energy increases, we see that the temperature of the substance is also going to increase, as we see here. Now, if we take a look here, not all of these particles here are going to have the same energy, right? Or excuse me, they're not all going to have the same speed, we can say. And if we take a look here at figure 2.24, it's actually going to be a distribution of speeds, as we see here. And as the average kinetic speed increases, so is the temperature. And that's what our graph here is depicting for us. It goes from 300 Kelvin to 1000 Kelvin to 2000 Kelvin. Now, how about if we wanted to measure that kinetic energy? How can we do so? Let's take a look at that now on the next slide. There we are. Kinetic energy of molecular motion. Now, each particle is going to have its own kinetic energy that's going to be associated with it. Now, if we want to find the total kinetic energy, we can do so through the following equation, as we see here. Now, if we want to find the average kinetic energy of a gas particle, we can do so through the following equation. And this constant here is one that often comes up, which is the Boltzmann constant. Let's just take a read here.